Okay, I think you can clearly see that in this model, the training and testing both are pretty low. So training accuracy is also very low, and the testing accuracy is also fairly low. So we have a very basic model to start with. Okay, we'll introduce some new jargons as we go along, but it's actually called an underfit model. But this is a very poor quality model to start with, because on the training data also we are getting a very low performance. That means it's like saying you have not studied well on training, right? So when I was teaching you something, when we were learning some new topics, you didn't study well from the textbook, so you're struggling there. And even when you're testing, when you're evaluating yourself on a unseen question paper or a mock question paper, you're struggling there also. So training accuracy is also low, testing accuracy is also low. So this is what we are able to see here. So this is what we call an underfit model, very poor quality model. And now we can compare. Okay, so now this is our very first machine learning model, and now we can compare. And you can see there's something called model.fit we use. So we've talked about it in the beginning of the session. If you remember, I told you that this is what we do as part of model training. So next time when we talk about training the machine learning model, we are using model.fit. So this is that model.fit that we are actually kind of using here overall. So as part of model.fit, you can see that we take the data and we are able to create the create the machine learning model, and we are able to evaluate the accuracy of the machine learning model, and this turns out to be a highly underfit model, very poor quality model. And now we can incorporate the second feature. If you remember, after TV, radio was the most important feature. So now we can experiment, but this is the process of experimentation. Okay, so this is the process of experimentation. So now we can incorporate uh, the radio feature, and now we can take both the TV and the radio feature, and we can check how the model has improved if I consider both TV and radio. So when I consider both TV and radio, we can run the code. Everything will remain the same, nothing will change, and we can comparatively see that when I incorporate both these inputs, whether I'm able to build a better quality model or not. So we can just run the code again, and you can see that we've got a better quality model because the training accuracy is higher and the testing accuracy is higher. Isn't that what we want when we are learning something? Isn't that the objective? Because when we learn something well, ideally we should perform better in the training. It's like saying, if I ask you some questions in the class, if you're listening to what I'm saying, if you're hearing what I'm saying, everybody should be able to answer what I taught you today, right? But at the same time, if I give you some exercises, which we will start with in the next phase, we'll do some exercises. If I give you some new questions, you should still be able to answer that. So both are important. So training accuracy means how well you are able to understand what I'm teaching you. But can you remember what I taught you? Can you solve the same exercises? Like if I give you the same problem, can you solve it? That's training accuracy. Testing accuracy means if I give you a different data set, can you solve it? I mean, that's like generalization. So I mean, you don't just memorize and like remember what I taught you. You don't memorize it. Like night before the exam, you memorize the topics. That's useless, right? But you understand what I taught you. So if you understand what I taught you, then even if I give you a different data set, you will still be able to answer it. So that's the whole idea. And this is the concept. And this is what makes machine learning a very highly experimental domain, because you see how we're experimenting with different features. So we started with only a single variable called TV. Then we took more variables and we tried to build different models in a very exploratory manner, and we are trying to see which one is better. See the idea? And initially, I was talking about Jupyter Notebook. See how this is. You cannot script it out. So when you're doing model development, you can't just write a single Python script up from scratch. You need to run the code. You need to execute multiple blocks, see which one works the best, where you're getting the best scores. Once you're confident, then you will transform this into a script. So this is why the exploratory development mode that Jupyter gives you is very helpful, because you try out different things. Maybe here, let's say I've got two features, TV, radio. Maybe you feel the need that I need to create a new feature. And oftentimes in data science problems, you might want to create a new feature, a new calculated feature. Something, some kind of a computation, some kind of a calculation using two or more features, you create a new variable. Okay, and you want to use the third variable. But you have a hypothesis. You have a hypothesis that, okay, I think that third variable is a good feature, but you don't know that yet. How do you test it? How do you test your hypothesis? So you create the third feature. You create a new feature called, let's say, x3, and x3 is some kind of mathematical computation of something, whatever. You create a new feature called x3, build the model, and compare the accuracies. See the train accuracy, see the test accuracy. So did it improve the model? If it did, well, wonderful feature. It's a good feature. Because remember, we are always working on correlation, not causation. So if you are able to create variables, if you're able to find correlation between the inputs and the outputs, and if that leads to a better model, that's all that we look forward to. We are ultimately trying to create a good quality models. This is the model.predict we can do. So if you see my code, this is the prediction. So if you want to do a prediction, you can just do model.predict. So there are two parts to it. One is .fit. .fit is how you build a model. You can try different algorithms, and you can do a fit. You can build a model, and you can go back and do a .predict. Okay, if you want to evaluate you want to use that model for a new data set. So if you have a new value, you have x new, and you want to do a prediction, you will simply do model.predict. Right now, what I want to do in this part of the conversation, I want to also show you how easy it is to use a different algorithm. Okay, so what I did in this part of the code is I used something called linear regression. It's the most basic algorithm that we are starting out with. One of the other things about linear regression is that it is usually um, it is a very baseline model. Think of it as a very baseline model, and it's absolutely possible that for certain types of data, it may not give you very good results. Right. So here it's a very simple data set. We have input X, we have output Y. It's a very straightforward data set we are working with. So linear regression did give us 80% and all, but as I told you, there can be certain types of data patterns which are inherently nonlinear. And if you're dealing with inherently nonlinear data patterns, then linear models will not work. You need nonlinear algorithms. And for that, we can try out different algorithms and see which algorithms are giving us the best results. So there are mainly two core ideas that we are working with. If I just switch the conversation to some of the things that we discussed, some of the things that we did. So there are broadly two core ideas, if you see. So one is we are trying to take different variants of data. So we are trying to modify the data. This is exactly what we did, right? We tried to take a different data. We have TV and sales, and we tried to create, we tried to take TV and radio, and we are trying to modify the data in different ways. We're trying to select the most important features, remove the least important features. Like if you remember, we did not take newspaper. That is one part. We are trying to modify the data, keeping the algorithm constant. Now what we will do, and we achieved some success. I think you saw that when we took TV and radio, we got a better result by taking the same algorithm. Now what we'll do is we'll keep the data constant, but we'll modify the algorithm. We will use a more powerful algorithm. Right now I use linear regression. Now I'll give you another demo where I'll show you gradient boosting, a more non-linear algorithm, and with that I will get a better result. So the objective is to build a good model. And what are the two components of a model? Data and algorithm. Okay, so you can use a better quality data, or you can use a better quality algorithm which is more robust, which is able to represent the patterns in a more generic way, or you can use a combination of both. And this is the experimental part of machine learning I was talking about. This is the part that takes the most amount of time. And as we go through all the case studies, and lots of case studies we will see as we go through the sessions, as we go through all our case studies, I think this is one area that we will try to cement. I think the having the right thought process, to think of exercises in this manner. So how can you look at uh, a wide variety of problems? How do you figure out what kind of data to take? How to try out different algorithms? And this is the exploratory part. Okay, so you try out different permutation combinations, and you narrow down to the ideal set of data and algorithms. And once you and build the final model. Okay, so here let me give you an example of using a different model. So I think until here we already did. So just to clarify, just to compare the results, I think we are pretty sorted with this part. See, we separated the data, used linear regression, training accuracy, testing accuracy. So we are sorted. Now what I will do, I will use the exact same data. I don't need to do X train, Y train anymore because that's the standard. I will use the exact same data and I will just use a different algorithm called, I don't need to type out, I can always use Gemini, but that's okay. I think this is, I think once you do some practice, this is becomes back of the hand stuff. It's a regressor actually. So, and I'll just say from SQL on ensemble import gradient boosting, look at the magic. Can you see the magic? So Gemini understands, look at this. I mean, it's almost incredible to even talk about it. Gemini understands what I'm trying to do. Can you see? So it understood in the previous cell, I was actually showing you a demo of linear regression. So, and Gemini somehow understands. Gemini is Google's language model. So it somehow understands the context. It understands that in the previous cell, I was building a model using linear regression. And the moment I import gradient boosting regressor, it understands that, okay, most likely Sayan is trying to do this. Most likely Sayan is trying to replicate exactly this pattern, this time using gradient boosting. Okay, it guessed it right. That's fine. And if I hit enter, it will further give me the testing. Can you see? Incredible, isn't it? I didn't type a single line of code, by the way. It's all generated by Gemini. Anyway, so now what's going on here? So we have the same X train, Y train, X test, Y test, because remember, my training and testing data is the same. Okay, so my training and testing data is the same because we have the same textbook and we have the same mock question paper. We have the same textbook and we have the same mock question paper. So this is my training and testing data that we have. And only thing is that we are using a different algorithm. So the only thing right now is we are using a different algorithm. So you can see that we are using a different algorithm here, and we are using something called gradient boosting regressor. So this is a different algorithm that we are actually using right now. And look at the magic that will happen right now. The moment I use a different algorithm, you will see that my results will be a lot better. I will get a lot better results. So control enter, you will see 99% and 97% straight away. Okay. It sounds magical, but what is going on behind the scenes is actually non-linear regression, because all this while we discussed about linear regression. So what you are seeing on the screen right now is actually non-linear regression. So it's not trying to find the best fit line, but it's in a way trying to find a kind of a non-linear mathematical surface. That is what is doing behind the scenes. So this is the big part of what we'll try to do in real world scenarios also when we build machine learning applications. You will have to constantly look at your data, figure out what are the different types of features you can take, identify flaws and defects in the features. There can be some missing values, outliers. So try to clean your data. So that is also a big part of what a data scientist will do, right? And honestly, much of these tasks have become very commoditized because with language models like Gemini and Copilot and so many easier ways of getting things done. So there are libraries that we have for everything today. But yeah, but this is just to show you a flavor of how things are done. You try different models, you find out their scores, you try a different algorithm for the same data. A different algorithm is giving you a better model, and this is a much better model than what we had before. So this is what and there are many. There are other algorithms you can also try out. For example, I can maybe create one more code cell, and this time I want to use. Okay, you know what? You don't even have to type out. Just go and use a comment line and say, uh, build a model, build a model using random forest classifier. So in case you forgot what is the syntax to import, even you forgot the import syntax also, so you can actually say, build a model using random forest classifier, using random forest. Sorry, not classifier, regressor. And if you just do this, wow, amazing, right? Gemini will even do the import package for you. So last one, I at least took some effort to write the import package. So here I just put a comment line, build a model using random. And see, this is not a random response. It's not a random response. It actually gives the response with respect to my code. It is not a random response. If you see, even the variable names are the same. Even the model 2 is exactly what I used. And that is why I say it's very powerful, because it's so the code editors of today are very context sensitive. They're context sensitive and they understand the code base. And the moment you try random forest, you see it's even better. The test R square or the test accuracy is even higher, 98%, which is great, right? So this is the way we iterate. This is the way how we, as I said, we try out different variations of data. We try out different types of algorithms, and we try to figure out which algorithm is actually giving us the best results. And I think based on what we saw here, the random forest regressor is giving us the best model because the test accuracy of this model is the highest. We're getting 98.61% test accuracy. That's what we're getting. There are some further concepts that we will study along the way, but before we get any deeper, there is one more very important topic, important concept that I've generally discussed, but I want to kind of cover it a bit more conceptually. Just this is a 5 minute concept that we will see: overfitting and underfitting. I might have mentioned that term a couple of times already, but let us understand that a bit more in detail. What is overfitting and what is underfitting? We are able to see overfitting and underfitting uh, being explained in this particular diagram. On the left hand side, you see model error. So error is nothing but 1 minus accuracy. So that is how we understand the meaning of error. You can see this is 1 minus accuracy. And along the x-axis, you see something called the model complexity. On the left-hand side, you have a overfit model, underfit model, and on the right-hand side, you have something called an overfit model. So what is underfitting? What is overfitting? So underfit model is that kind of model where there is no learning happening. That is what we refer to as underfitting. So what is underfitting? Underfitting is a condition where there is absolutely no learning happening. That is what underfitting is all about. There is no learning happening in underfitting. The training error is also very high and the testing error is also very high. So both the errors are high. The training error is also high. The testing error is also high. So both the errors are high in underfitting. So there is no learning happening, right? Obviously, you can imagine that it's something similar to this we saw when we tried to build a model using TV and only the TV feature. So when we built the model using only the TV feature, we saw something very similar to underfitting happening, right? That's what we saw. What is overfitting? Overfitting is where the training error is very low. That means you learn the patterns very well on the training data. On the training data, you learn the patterns very well. But on the unseen test data, we make lots of mistakes. That is how we define overfitting. So underfitting is where both the errors are high. So training and testing, both the errors are high. So the model performs very poorly on training, very poorly on testing. Overfitting is where the training error is low, testing error is high. So that means it's kind of like rote learning. No? Rote learning is where we memorize something in detail. We try to memorize something. Rote learning. So you learn the training patterns very well. You don't make any mistakes here. So training error is zero, almost close to that. But have you really learned anything? Maybe not. If I give you a new exercise, you struggle. Even test data, you struggle. So that's overfitting. Both are bad. So what we need is we need to create a good fit model. And good fit is that zone where we have the lowest test error. Lowest test error basically means the highest test accuracy. So when we have a model with the lowest test error, that means typically the test accuracy is the highest. That is what we mean by having a low test error. So low test error basically means we have a high test accuracy. So this is the objective of machine learning. So we try out different permutation combinations of data. We try out different permutation combinations of algorithms. We try out different algorithms. We try linear, we try random forest, gradient boosting. We try different algorithms, and we'll see that in a lot more detail. We have a lot of way to go. And we build different models, and then we evaluate which model is giving us the best performance. So we have model 1, which is giving us this much accuracy. Model 2 is giving us this much accuracy. So we compare the performance across the different models, and we see which model gives us the best performance, and we try to build the most good fit model. So that's the way how we go about it. Now, if you relate this to what we discussed in our conversation already, you can see We started our conversation with the TV feature, and if you remember, when we built the model with only the TV feature, we were getting a highly underfit model. Why were we getting a highly underfit model? Because the training and the testing scores both were extremely low. The training score was also very low, and the testing score was also very low. So that is what we refer to a highly underfit model. Then we took TV and radio. If you remember, we were getting something like 60%, 40%, highly underfitting. And now we take radio feature. We take one more feature. And when we take that extra feature, we are getting a better quality model, right? You can see the training score is also high and the testing score is also high. So by incorporating that new feature, by incorporating that one extra feature, we are able to build a better quality model, a more good fit model. If I have to be more technically correct, we are able to build a more good fit model. This is what we call a more good fit model because we are getting a higher accuracy in training and a higher accuracy in testing. There is another very important concept I would like to talk about, and the concept is related to the concept is related to the concept in this case is related to the idea of um, the relative performance. So overfitting and underfitting are both relative techniques. So when I say that we are trying to build a good fit model, remember the good fit is always relative. So we are always trying to build a model that is relatively more good fit. That is the core idea. There is nothing called absolute good fit, but we are always trying to make it better. We are trying to always build a model that is relatively more good fit. And that is an important idea that I want to clarify. So imagine here I'm getting 89%, 89%. This is the same thing I was demonstrating here, right? If you remember, we got with linear regression, I was getting 89% and 89.47%. We got a decent model, right? Anybody who sees this model in the first glance, they will say that, hey, this is a good quality model. It's a good, it's a good fit model. But you know what? This is not the best model. We can make it better. That's what I mean to say. We can make it better. So we can take this particular model and we can make it better than this. It is always relative. The idea is always relative. So with gradient boosting, if you see, compare this with this is what we call a more good fit model. Because the training score is higher, the testing score is higher. So in both the parameters, you do better. This was already a good model. It was a decent model. But the next model that we built using gradient boosting, keeping the data the same, the algorithm is different this time, we are getting a better quality model because the training score is higher and the testing score is higher. And that's the way how we understand the concept of overfitting, underfitting, and good fit. These are some very, very common terminologies that you will hear in machine learning and very, very common terminologies that you will hear. I think this is another couple of very interesting diagrams you will find which helps us solidify this concept because this is another way to look at it. All of you take a look at it. This is pretty much what we talked about. You can see on the left hand side we have an underfit model. That's what we are doing in regression, right? We are trying to find the line of best fit. Remember, it doesn't always have to be a perfect fit. It has to be a best fit. So on the left hand side we see an underfit model. Underfit model is where we are not able to represent the patterns perfectly. That is what we call an underfit model. And on the extreme right hand side we are seeing an example of an overfit model. This is a model where we are actually learning the patterns perfectly well. On the left hand side, we are not able to learn the patterns at all. That is perfect underfitting. On the right hand side, we are learning the patterns too well. So whatever model we are building, it is basically passing through all the points. That means on the training data, it is doing a very good job. And this is what we refer to as overfitting. And somewhere in the middle, we are seeing an example of good fit. Good fit is like an okay kind of model. We are able to like reasonably do a decent job. This is a pictorial understanding of what is underfitting, what is overfitting, what is good fit. And this is the reason why, if you remember, that using linear regression on the sales data set, it didn't give us good results because it was most likely underfitting. Although we saw 89% accuracy, R squared is what we were getting, but still When we did gradient boosting was doing something like this. It was a non-linear model. It was a polynomial model that we were building. So this is what happened behind the scenes.